Hello friends, welcome my channels. Today I want to discuss field extensions and ring theorem. So friends, I start revision of ring theorem. A ring is a set R together with two operation plus and multiplicative star which has the following properties. R is a commutative group under plus multiplicative identity. There is an element 1 such that r dot 1 equals to 1 dot r equals to r for all r belongs to r, capital R. R is associative under multiplicative operator star. The operation star distributes over plus. A star first bracket b plus c equals to a star b plus a star c. A plus b star c equals to a star c plus b star c. So friends, this is the total ring theorem property. The isomorphism theorem of rings. Fundamental homomorphisms theorem. If phi such that R tends to S is a ring homomorphism, then curve phi is an ideal and image phi are isomorphic to R by curve phi. Then this is the diagram where phi is any homomorphism, R is a ring, and I is a curve phi, kernel phi means nullity. A nullity is the ideal, and image phi greater than equals to less than equals to S means image phi is always smaller or equal to S, and quotient process Q R divided by curve phi is equal to quotient ring, and G remaining isomorphism. The second isomorphism theorem for rings. Suppose S is a subring and I an ideal of R, then the sum S plus I equals to S plus I. S belongs to S and I belongs to I is a subring of R, and the intersection S intersection I is an ideal of S. The following quotient rings are isomorphic. S plus I divided by I isomorphic to S divided by S intersection I. Remember friends, S is a subring and I is an ideal of R. This is the second isomorphism theorem. Very interesting. And this is the total diagram. S intersection I and S plus I and R. So friends, whatever we have learned S plus I, quotient of S plus I R divided by I, isomorphic to S divided by S intersection I. This is the quotient ring. And now you have to learn that field, and after that PID, UFD, and in integral domain and commutative rings and all rings. Okay, in here you must remember that PID contains fields, UFD contains PID fields, and integral domain contains UFD and PID and also a field, and commutative ring integral domain UFD PID all a field all are commutative ring. So friends, every fields is a PID and every PID is UFD and every UFD is integral domain and every integral domain is a commutative ring and every commutative ring is a all ring. The third isomorphism theorem for rings. This is called also Fleischmann theorem. Suppose R is a ring with ideals J subset of I, then I divided by J means quotient Ij is also an ideal of R by J. Then R by J divide by I by j equal isomorphic to R by I. The fourth isomorphism theorem for rings, let I be an ideal of R. There is a bijective correspondence between subrings and ideals of R by I and subrings and ideals of R that contain I. In particular, every ideal of R by I has the form J by I. For some ideal J satisfies I subset of J subset of R. Extensions field. Definition. Let F be a field if F subset of K, then we say K is a extension field of F. Means F contains K. Means all the element of F belongs to K. The three most important classes of fields we will encounter are the following. Number fields. Number fields. A number fields K is any subfields of C. As any subfield of C contains 1, it must also contain Q. The number field most commonly studied are those where every element is algebraic. Finite fields. A field having only finite many elements. If K is finite, then the kernel of the unique homomorphism Z tends to K is a prime ideal. Since Z is infinite, so in particular K contains a subfield isomorphic to Z by P is equal to Fp for some prime P, and hence we can consider K as an extension of Fp. Function fields. Certain extensions of the field Cx. Specifically, suppose we have an irreducible polynomial in F belongs to Cxy, which is not a polynomial in X alone. Since it is irreducible in Cx, y, we know that it is irreducible in C box X box y. Hence, by the generalized Gauss lemma, we have that F is also irreducible in F equals to Cx, the fraction field of Cx. In particular, this means that the ideal F belongs to F box Y is a maximal, and hence F box Y divided by F is a field. Algebraic or transcendental extensions. Definitions. Let F be a field and let alpha belongs to K such that K contains F. We say that alpha is algebraic over F if there is a polynomial over F which is satisfied by alpha. That is, if alpha to the power n plus an minus 1 alpha to the power n minus 1 plus a1 alpha plus alpha equals to 0 for some a0, a1 and an minus 1 belongs to F, we say that alpha is a transcendental over F if it is not an algebraic over F. We can think of the two possibilities in terms of the evaluations of the homomorphism, specifically lemma. Let F subset of K, means K contains F, be fields with alpha belongs to K, then if phi alpha such that f box X tends to K and fx equivalent to f alpha, we have alpha is a transcendental if and only if psi is a injective, or more specifically if the kernel of psi is 0. Irreducible polynomial definition: let f subset of K, means K contains f, be a field with alpha belongs to K. Further, let psi alpha such that f box X tends to K and fx equivalent to f alpha, we then know that the curve psi alpha is a principal as f box S is a principal ideal domain. So in particular, it is generated by a single element f alpha x belongs to fx. Because we know that, friends, that principal ideal domain it has one generators, so this generator should be maybe f alpha x. But because K is a field, we must have f alpha x is irreducible, because otherwise K would have a zero divisor. Hence, f alpha x is the only irreducible polynomial in a ideal f alpha x, because every element of the ideal is a multiple of f alpha x, and we call f alpha the irreducible polynomial for alpha over f. For example, let alpha equals to root over I, then the irreducible polynomial for alpha over q is x to the power 4 plus 1. However, q box I, the irreducible polynomial, is x square minus 1, and what is more, q box I, x to the power 4 plus 1, is not irreducible, as x to the power 4 plus 1 into x square plus 1 into x square minus 1 box f alpha. Connection between f box alpha and f alpha lemma. Recall the f box alpha is the ring and summation an alpha to the power n such that an belongs to f and is the smallest ring containing both f and alpha, and we then have f alpha is isomorphic to the field of fractions of f box alpha. In particular, we have that if alpha is transcendental, then f box x tends to f alpha is an isomorphism. If alpha is a transcendental, then f box x tends to f alpha is an isomorphism, and hence f alpha is isomorphic to the field fx of the rational functions. Definition: let f alpha be the smallest field containing both alpha and f. Similarly, f alpha 1, f alpha 2, up to f alpha n, and be the smallest field containing alpha 1, alpha n, and f. Field extension as vector spaces. Theorem: let alpha be an algebraic over f, and let fx be its irreducible polynomial. Suppose fx has degree n, and then 1 alpha alpha to the power n minus 1 is a basis for f